Hello, we are going to start the second presentation given by Silvia Franceschi from Hydrology from Italy. This presentation will be analysis of extreme events with the HortonMachine tools. So, Silvia, whenever you want.
Thank you. Thank you, Mario, for the introduction, and welcome to everybody. Welcome to this presentation. In this presentation, we will see some interesting tools of the HortonMachine library suite to, okay, I'm here, to analyze extreme events. So let me first introduce myself. I'm Silvia Franceschi. I'm a co-founder of Hydrologies, which is a very small Italian engineering company placed in the northern of Italy. And I'm an OSGeo charter member. Basically, I'm an environmental engineer specialized in hydrology, hydraulics, geomorphology, and forestry, with a PhD in mountain environmental and agriculture. And in hydrologies, sometimes I used to develop scientific models contained in the HortonMachine library in the fields of hydrology, hydraulic, and forestry. So what is this HortonMachine library? The HortonMachine library is an open source geospatial library focused on hydrogeomorphological analysis and environmental modeling. It has been developed starting from 2002 at the University of Trento Department of Civil and Environmental Engineering, and it has been supported over the years by the same University of Trento, in particular the Professor Rigon, and of Bolzano with the Professor Tonon, and maintained by Hydrologies. This is a bit of history about the HortonMachine library. Now, the HortonMachine library is available as a standalone, as a set of standalone applications, but from 2015, it is also integrated in the gvSIG desktop as a spatial toolbox. The plugin is available to the gvSIG update manager. You can see here some a screenshot of how to install the HortonMachine, the spatial toolbox, and what you can see from the in gvSIG as the HortonMachine menu. So the HortonMachine suite provides tools to analyze different environmental processes like extreme floods, debris flow, large wood floods, shallow landslides, vegetation and forest analysis, and meteorological data interpolation. It is possible to do more things rather than only analysis only. That is not only, but definitely that analysis of environmental processes, which are the urban network design and verification. For example, it is possible to design and verify up and do the verification of the real network of aqueducts, water supply systems, and wastewater for rainfall in urban systems. And we have tools for digital field mappings. If you have time, just go and see the presentation that I had before on GEOPAPARAZZI application of digital field mapping. And then it is in general, there are tools to handle geospatial data like spatial databases, raster calculator, and we also support a full scripting environment. But we will see now what it is the content of the HortonMachine suite. The HortonMachine suite is available as a zip archive containing all the requested dependencies for Windows and Linux. And this provides a set of applications to work with environmental and geospatial data. In particular, there is the spatial toolbox, the DB viewer, some tools to interact with GeoPaparazzi, the GeoPaparazzi viewer, GFORMs, and SLD, the GeoScript and MAPCALC and the some other tools to handle geospatial data like QUICKFOLDER and WMS to GeoTIFF converter. Let's see just a quick look of these tools of the suite. For example, the database viewer, it is possible to create or load existing databases. You will see here the list of the tables, and you can easily do some operation with with just a mouse click, count the table record, select, write the select statement. If you select this one, select statement, automatically the select statement will be written in the SQL editor, and then you can personalize it if you want to add some information, like, for example, a where condition or so on. And here is a view of the first part of the table, only a subset of the table, not all the table. It is possible to have the SQL history, and then to have templates to handle different editors and have different queries open, and visualize a quick view of the table in 3D. And if it is a geospatial table, it is also possible to view the table, the geometries, to visualize the geometries in the table. Then there is the GeoPaparazzi viewer, which is a very simple application to visualize the data contained in a GeoPaparazzi project. For example, you can see the list of the pictures. You can see evaluate the picture, the position in the map of the pictures and the notes, and the GPS tracks. We support a full GeoScripting environment based on Groovy and GeoScript. Recently, we also developed some tools again to interact with GeoPaparazzi. For example, the GFORM, which can be used to create complex forms for GeoPaparazzi and use them directly in the digital field mapping application. And then we have the tool for the map calculation, geospatial map application and calculation, and in particular do complex operation on raster maps. For example, in this case, which is possible to extract from the DTM only the areas which is over than a given threshold. And this tool is quite young, so unfortunately no documentation is available yet for this tool. But it is very simple, also the syntax. We developed this very quick folder viewer, which shows the content, the geospatial layers contained in a folder. You can style them, visualize or not visualize them, and visualize the attribute table and main information, like the projection or so on. The SLD creator, again, is done to make the data for the digital field mapping application GeoPaparazzi. Here you can style both shapefiles and data MB tiles, raster MB tiles, and you can define both the style and the labels. And then the last developed one is a very easy, it's very simple tool to convert the WMS to GeoTIFF. It is done to facilitate the user in the use of web services, and sometimes these services have to be available also offline, or you can have a problem of connection and so on. So you need to download the GeoTIFF, and in this case, it is possible to define the server, select the layer, the projection, the format, and then select, define the image, the GeoTIFF parameters, the dimension of the image, the area of interest, and finally the name. And then you convert the WMS and download GeoTIFF. And now we have, and the final is the Spatial Toolbox, which is definitely the first one, which I mean, it is the one which contains the scientific tools of the HortonMachine library. In particular, the Spatial Toolbox is a graphical interface with a panel containing all the module list in the left side. If you select a module, in the left side, you will see all the parameters needed and input and output in the right part of the panel. Then you can configure the running option if you want to run the model, or if you want to create a script with this configuration, or load a script to run it. And then you can define some running parameters, which are the debug mode and the allowed process memory. Let me see a bit better the Spatial Toolbox. This is the list, part of the list of the tools available. As you can see, models are grouped by categories and subcategories. And in particular, we have these 4 categories, main categories, which are the HortonMachine, which contains tools for geomorphology analysis, as you can see here, dam manipulation, geomorphology, hill slope, and so on. Then you have the raster and vector processes, mobile tools to interact with GeoPaparazzi application for digital field mapping, create data, and then convert the data contained in the GeoPaparazzi project. And then there is the LESTO library, which is developed with the University of Bolzano and contains tools to interact and analyze high resolution LiDAR data, especially for vegetation and forestry analysis. Let's see now some of the tools that can be used to analyze extreme events available in the HortonMachine suite. The first tool, and these tools can be also used as base to define hazard map for natural hazards like flood, debris flow, landslides, and large wood floods. The first model that we analyzed is the possibility to extract from the HortonMachine the maximum discharge. The maximum discharge means the evaluation of the maximum discharge for a given precipitation, which can be done, which can be a real past event you want to simulate, or the extreme events evaluated through the statistical analysis of the historical series of precipitation, the so-called rainfall intensity duration curves, as suggested by the EU flood, European Flood Directive, for defining the return times of the events. First of all, if you want to evaluate the maximum discharge, first of all, you have to do some geomorphology analysis to extract topographical parameters from a digital terrain mapping model. In particular, you have to do a pit detection, the definition of the drainage directions, which can be done using a simple DH method or a DH with some correction, considering the general hill slope, the general gradient of the hill slope, and the definition of the main network through the extraction of the catchment for a single outlet. Then the model needs also some hydrogen morphology analysis parameters, so which can be derived through hydrogen morphology tools to evaluate some hydrological and hydraulic parameters like distance to outlet, rescale distance, gradient of hill slopes, topographic index, and so on. Here, for example, you can see an example of the topographic index and the rescale distance to outlet. The statistical analysis of precipitation, the IDF curve, the parameters of the IDF curve can be, usually they are available from public administration, local public administration, or from other studies. But if you don't have them and you just want to create this from your own rainfall station or something like that, you can do it using the using your own tool, but also developing something in the scripting console. Like here, you can develop the tool and create the IDF curves for different return times. Finally, you have to run the model from the evaluation of the maximum discharge, which is called PICFLOW. PICFLOW is a semi-distributed hydrologic model based on the geomorphologic instantaneous unit hydrograph and the weight function. You can calculate with it the maximum discharge. The geomorphologic instantaneous unit hydrograph is calculated using the width function, and the precipitation, the hypothesis is that the precipitation yetograph is constant, and the model separates superficial and subsuperficial fluxes. Superficial fluxes is evaluated using a Dunyan mechanism in this only in saturated areas, and unsaturated areas contribute to subsuperficial fluxes. And here is an example of the result, the different discharges for the discharge for the different return times. This is a map of topographic index, and this is a map, for example, of the geology to consider the saturation of the basin. Oh, sorry. Okay, this is all about the maximum discharge. But once you have the maximum discharge, you have to you can go on with this discharge and do your elaboration for hazard mapping. If you just have liquid discharge. But if you have debris flow, like in the mountains where we are, you can also use some other tools to evaluate the solid component of the debris flow. In particular, in the HortonMachine, there are tools to evaluate the possibility for debris flow to start along the stream network and propagate downstream, or the possibility to for the debris flow to start from hill slopes outside the stream river, reach the river, and then propagate downstream, and then finally extract the hazard map for debris flow on the alluvial fan. So one of the tools, for example, in the HortonMachine is the debris trigger CNR, which identify the triggers along the channel network based on the Zimmermann equation. This equation is the main input of this equation is the total contributing area, and a threshold on the total contributing area is fixed at 10 square kilometer, because usually higher value of total contributing areas or bigger basins usually generate processes of bed load instead of debris flow. And then the local slope. Local slope is local will be if local is greater than the threshold calculated with the Zimmermann equation, so the pixels are considered as possible triggers along the network. Pixel with the slope greater than 38 degree can be excluded from the analysis because usually the soil over this gradient, the material available is very few. This is an example of the graphical interface of the tool, the debris trigger CNR. You have to insert the map of elevation, the network, and the total contributing area. Then you have to specify these two thresholds, and then you have the output trigger map. Here is, for example, an analysis done for an entire valley in Trentino of the triggers along the network. Then we want to evaluate the contribute of the hill slopes. First of all, we have to understand if we have landslides, shallow landslides on the hill slopes, and in particular, if the hill slopes are stable or not. And we can use this model, which is SHALSTAB, which evaluates the hill slope stability based on the SHALSTAB algorithm developed by Montgomery and Dietrich. It uses the theory of infinite slope with a simplified hydrological model. The resulting equation shows the ratio between the contributing area and the length of the boundary in the point. And it is the stability is a function of the soil density, the water density, the angular slope, the friction angle, the soil transmittivity, and the effective rain. The output of the model is the map of the critical precipitation in each pixel and the stability map of the given precipitation, like here. So if you have pixels which are not stable, then you can evaluate if this pixel contribute to debris flow, can contribute to a debris flow. So if there is the possibility for these triggers on the hill slope to reach the network and go downstream. In particular, only unstable pixel on hill slope can be considered as triggers, and only triggers near the network can reach the network. So usually we insert an average distance like the medium length of the superficial landslide over the areas, which is considered 25-50 meters. The tool to use is the debris vandre, and this in particular in the path from the hill slopes to the channel considers where the slopes are greater than 10 degrees, the movement continues unconditionally, and the soil along the track is scored and added to the eroded material from the initial landslide site. Where the slopes are between 4 and 10 degrees, the material comes to a halt over the runout distance, and the soil along the track is not cumulated. And the runout distance is calculated using the Vandre formulation. Where slopes are less than 4 degrees, the material comes to halt over the runout distance. This is an example of the application of SHALSTAB and debris vandre. It is a map of unstable area in the basin at various return times. As you can see here, the yellow, green, and red pixels. Then debris vandre can be used also to evaluate the runout distance of debris flow inside the network. So once we have the triggers inside the network and the contribute of the hill slope in the network, we can use the debris bundle to propagate the debris flow downstream in the network with this condition. Where slopes are greater than 80 degrees, the movement continues unconditionally. Where slopes are between 3 and 8 degrees, the debris flow comes to halt over the runout distance. And where slopes are less than 3 degrees, the debris flow comes to a halt over the runout distance. This is an example of the map of the triggers and the path in green. This is a graphical interface of the debris boundary. As you can see, there are some information, some layers, some geospatial layers derived from the DTM, the map of elevation, the flow direction, the slope, the map of the triggers. If you have a map of soil and some parameters, and then define the output. And here is a better visualization of the triggers, where the triggers are, and the paths. And here is also a simulation of the hazard of the alluvial fan. For example, the green are not so hazard. From the A is the hazard, the dangerous fans, and then the yellow are the less dangerous fans. And you can see where there are the yellow, you do not have anything that comes to the alluvial fan. When you have the green, maybe something arrives at the head of the alluvial fan, and when you have the red, some important triggers reach the alluvial fan, like in this case. Then the last one tool dedicated to debris flow, which is definitely has the same name, but debris flow. It is based on the top run DF model, and it predicts the repository and the amount of sediment deposition in a torrential fan. The input parameters are the debris flow volume, the mobility coefficient, the starting point of deposition, and the digital terrain model of the area. It uses a simple DH algorithm and individual flow path following the steepest decretion flow. And a Monte Carlo iteration number is used to simulate lateral spreading of the flow in the area. And individual flow path is based on a random outflow direction calculated with the Monte Carlo iteration. This is an example of application and the graphical interface, and the magenta line here represents the a past event which we want to simulate. Regarding debris flow, I will also show you another use case we had here in Trentino, the 29th of October of last year. In a small town here in the mountains. In the valley in general, we got very high precipitation, and in this place in particular, we got 400-500 millimeters of precipitation in 2 days. Consider that we usually have a precipitation, average precipitation of 800, maximum 1,000 millimeters yearly. So definitely this is half of the yearly precipitation in 2 days. And in this place we also had two past events, one in 1882 and one in 1966. This is what happened, the post event, a picture of the post event, and these are pictures of post event. As you can see, a lot of debris and a lot of water everywhere, and unfortunately there are also they have been also problem in the houses. So in this case, the hazard mapping has been done 7 years before using the HortonMachine tools, and the map calculated with 200 years of return times showed that more than 1,000 of cubic meter of material could reach the alluvial fan, and in fact it was. And this is the map of the hazard map of the place. And obviously, you can also do a post-event simulation. As you can see here, this is a very raw post-event simulation with the debris flow. So you can see it is possible to simulate almost the areas which can be covered by debris flow. So this is all about debris flow. Now we can see the last phenomena, the environmental phenomena. I want to show you as extreme event, which is the large wood floods. The large wood floods consider a set of GIS tools, consisting a set of GIS tools for predicting the magnitude of large wood transport during flood events at any given condition within a river basin. We consider two main processes related to woody debris: the large wood recruitment from hill slopes and from bank erosion, and the large wood transportation along the network. The bank erosion also consider the presence of geology, if geology is erodible or not. This is the processing diagram. It is a bit complicated, but in fact it is only full of things. For example, we analyze extreme events for knowing the maximum discharges and the channel widening, the stability of the hill slopes and the connectivity of the unstable areas to evaluate the unstable and connected areas of the fluvial network. And besides this, we have to evaluate the vegetation parameters. The vegetation volume and dimension of available wood is evaluated, can be evaluated using two different approaches. The first one is the analysis of canopy height model with a semi-empirical model, or the analysis of high-resolution LiDAR data following a single tree model, which extract each single tree position, height, and diameter. Regarding the rest, the extreme events and the unstable area connected to the network provides area that provides large wood, and the vegetation information provides the volume and dimension of large wood, which can be used to evaluate the critical section and large wood volume. To evaluate this, we need also some information about the propagation, which can be derived through field data and monitoring of past event of large wood using a 1D hydraulic model, some information about bridges, dams, and sections. The tools for large woods is a step-by-step procedure, which the analysis of large wood follows a step-by-step procedure split in sub-modules, which can be derived in a pre-processing, considering the attributes of the network and the channel widening, the attributes evaluation, like the bankful width, dams, and so on, and recruitment and propagation processes, recruitment from bank erosion, from hill slopes, and propagation along the network. So regarding the processes, bank erosion is the process of bank erosion is evaluated using the pre-event condition corresponding to the bank fall width. Consider the flow event that occurs every 1.5 years. Inputs is the polygon of the extension of the bank fall area, which you can extract from the from digital maps or from field survey. The width ratio is calculated using a power law of the unit stream power, and some other power. The parameters of the power law can be derived from field observation and are input parameters. Here you can see a schema of the bank erosion. It's very small. Here is the result of the bank erosion. We also consider the geology, where geology is rock, it is not erodible. So there is no, like in this case, outside the yellow polygon, it is not possible to for the river to widen. The widening area is this one, respect to the blue area, which is the bank fall area. Then we have to evaluate the contributor of the hill slopes. So the hill slope, first of all, we have to evaluate the presence of precipitation. We can evaluate the vegetation parameters using an empirical model of canopy height model and the total stand volume, or using the analysis of the tools contained in the last part of the HortonMachine regarding the to extract the single trees from LiDAR data and canopy or canopy height models. In both cases, we evaluate the presence of vegetation on the hill slopes and the vegetation parameters, in particular the position and the height and diameters of the parameter, which have to be used for the propagation process. Here is an example. Here is the identification of the single trees in this area. And then from the hill slopes, you have to evaluate the stability of the hill slopes and the possibility to for this unstable area to reach the river and take some material to the some wood to the and give wood to the river. So we definitely evaluate the stability of the rivers with the Shellstab of the hill slopes with the Shellstab model, and a model for the downslope connectivity to understand if the unstable areas are connected to the stream network. And then from the stability coefficient, the downslope connectivity, we fix a threshold for which we define if it is connected or not. And from this, we extract the unstable connected area. This threshold is evaluated through field and literature data. These are the hill slopes, the definition of the subbasin, and the unstable and connected, the vegetation on the unstable and connected areas on the pixels. Okay, so these are all this is all the vegetation. This is the green here, the green triangles are the vegetation on unstable and connected areas, and in particular they are highlighted here. Okay, and finally, if you sum the contribute of the hill slopes in terms of wood and the contribute of bank erosion, you can find the total large wood recruitment in each section, and you can identify the section with more contribute with those which do not have any contribute or have only very few contribute on the with the large food. Then we have to propagate this contribute, that's this local contribute is routed downstream and using a simple Boolean transport condition using the ratio between the length of the log and the width of the sections, and the ratio between the diameter of the logs and the height of the water depth, the water, and using the post-event channel width, where the water depth is calculated through a one-dimensional hydraulic model using the peak discharge. So you use here everything, the maximum discharge, these tools for debris flow, and so on. And finally, after the propagation downstream, for each section, you can identify if it is a critical section for the transit of large wood or not. And if it is a critical section from the transit of large wood, some information about which kind of wood will stop there and the volume, the possible volume of the logs accumulated in the section, in each section is stored in the parameters of the shapefiles. And then you can do this map for all your basin and highlight your the critical sections respect to the other sections. So I think it is more or less everything from my side. There are other processes, but we do not have many time to discuss them. But if you have some question, you can just write to me or join us in our in the mailing list, also the mailing list of gvSIG, and in general all the information about the HortonMachine you can find in the HortonMachine website, hortonmachine.org, and there is also the link to download the standalone release of all the HortonMachine suite. So thank you very much for everything and for participating. Thank you.
Thank you very much, Silvia. Very nice presentation. We're going to wait a few seconds.
Thank you.
If there is any question at the chat.
Okay. Yeah.
Yes. And if there is anyone, people can answer at the mailing list, at the gvSIG mailing lists, or at your contact details. So we are going to wait. And it seems that is very clear. So we can, yes, we can finish here. And
thank you.
And if anybody wants to ask, they can do it at the mailing list, for example.
Yeah.
Okay. So thank you very much, Silvia, and thank you to all the participants.
Thank you to you and to all. Thank you. Bye.
Okay, thank you. Bye-bye.
Bye.